Physics, and today we're going to talk about how friction is fun. Woohoo!
Okay, so we talked before, earlier in the year when we talked about friction, we didn't use any formulas to find friction, but what we did talk about was net forces. And we could have a net force on an object, or we could have no net force on an object. And what happens is, we had an object sliding across some rough floor, and it was accelerating in a negative direction, or in plain English, it was slowing down. And it was slowing down because it had some frictional force on it. And we asked you before to find the frictional force, but we did it through net force. So today what we're going to talk about is what friction actually is. Friction is a force that opposes motion.
I would write that down if I were you.
Yeah. It's always in the opposite direction of motion. That's what we mean by opposes. So if this box was sliding to the right, friction would be then to the left. Now there is a formula for friction, and it's a really fun formula. So, force of friction. Now, when you write out your force of friction, your little subscript is going to be a script-looking F. Remember, that's a subscript, so it's like below the actual big force F. Is equal to mu, yes, mu, times Fn. Now, mu, it's a symbol that you've seen before. You look at your second best friend, the reference tables. We've used mu before for micro. We talk about micrometers or micronewtons or anything. It's a prefix that we put in front of some unit to give it some kind of extra meaning like small pieces of centimeters or meters. Well, today we're using it as an actual variable. It's mu, okay? Just mu.
It's how you pronounce it, but you're just doing, it's a Greek letter.
Right.
So you're doing kind of a scripty U.
So if you know your Greek alphabet, you're fine with mu. But anyway, so mu, mu, is a variable that we use in physics that represents the coefficient of friction. Now here's a great thing about mu. It has no units.
Woohoo!
It's the first thing that we've talked about this year that's what we call dimensionless, which means it has no units. So here's a good thing to actually think about. If we ask you to calculate a mu, and you give me back a number with a unit, you might be wrong, because mu doesn't have any units. And think about why that would be. Force of friction, Fn, times mu. If you divide this force of N to the other side, you would have a force divided by a force, which would be newtons divided by newtons, which cancels out the newtons, and all you have left is no unit.
So before we go any further, let's just remind ourselves what this Fn is. That Fn is our normal force. Now when we talked about normal force, we always said that it was perpendicular to our surface. So it is helping support this box that's on the floor. Now the other force I should add to my free body diagram, or my FBD, I know we're bringing up things that are way back in your head right now, but the other thing that I should add is that we have our force of gravity.
Remember, physics builds on itself, so everything we've covered before comes back now when we add something new to it. So now we're not talking about projectile motion anymore. We'll move past that stuff. That stuff will come back again later. But now we're going back to what we started talking about, free body diagrams and the force of gravity and normal force and all that other stuff. And then we're adding something new to that. So, Fg and Fn, how do those two forces relate?
You should remember that the magnitude of your force due to gravity and the magnitude of your normal force are equal. So we can say that Fg equals Fn since we're on a flat surface. We're going to get to what happens when we change that. But for right now, we're still on our flat surfaces. Those are still equal to each other.
So, how then do you calculate the force of friction in an object? Well, what you're going to do is, in a particular practice example, you will be given the surfaces that are in contact, and you would have to look up the mu between those two surfaces. Where would you look them up?
best friend.
Second best friend. So in your second best friend, you will see a table of coefficient of frictions. And it says the coefficient of friction between this object and this object is some number. Please notice that they are all less than 1.
I have
There is
best friend.
no coefficient of friction that is more than or even equal to 1.
So it's in the bottom right corner of your reference table. It says approximate coefficients of friction. And if you look at that, if you have your best friend in front of you, which you should, you'll see that there's 2 columns in there that we're also going to talk about. So it has our coefficients of friction, it has all those numbers, and it has these 2 words.
Kinetic, static. Well, what's the difference? Which one do you use and when? Well, kinetic means motion. So if an object is already in motion, you would use the kinetic coefficient of friction. This means sliding. When 2 objects are sliding past each other, like for example the stapler on the desk, I slide the stapler, that's kinetic friction because the object is moving. Static means stationary. So this is objects that are not moving yet, but they can start to move. But then the question is, well, what about rolling objects? What if I had a ball that's rolling across the ground, or a tire of a car? That's actually a very common question. A question could come up saying, what is the force of friction on a car driving wherever it is? Would you use kinetic or static? Notice we wrote in here sliding. If your car is not sliding across the ground, say you slam on the brakes and the car skids to a stop, that's sliding. Every other case is static. But please be aware, we wrote here not moving. Your car is moving. It's rolling across the ground. But if you break it down, you picture a tire hitting the ground. Every piece of tire that hits the ground actually stops on the ground and then pushes off and makes the car move forward. So every little tiny piece of that tire that hits the ground is stationary for a fraction of a second. That's why it's static friction.
So the other thing that we can think about and that we can look at on our reference table is we can pick one of these situations. So we're talking about a car driving, so let's look at rubber on asphalt. And they will specify which one they are talking about when they give you a problem, whether they're talking about asphalt or concrete. And we're going to look at a dry situation. So it's a nice, beautiful day. When we look at those numbers there, for kinetic, we have 0.67 for our coefficient of friction. And for static, we have 0.85. So our static coefficient of friction is larger than our kinetic. And if you look at any of those other numbers there, you will see for each situation, the static is larger than the kinetic. The reason for that is because if you try and move something, when you first are trying to push on it, it takes a lot more force to get it to start moving than it would if you were just to continue keeping it in motion. So it is harder to start moving it, therefore that means there had to have been more friction acting against you, trying to make your life harder.
What this means is the static friction is always higher than the kinetic friction. The reason being, if we go to another slide here, the reason being, if we take, let's say, a textbook on top of the table, if you take a microscope and zoom into that connection between the textbook and the table, even though the textbook feels really smooth and the table feels really smooth, they're not that smooth microscopically. So if this is the bottom of my textbook, it's got some bumps and grooves on it microscopically. The table also has bumps and grooves in it. So what happens, as that textbook starts to sit on that table, these bumps and grooves start to actually connect and they kind of sink into each other. So in order for me to start the textbook to move, I have to kind of break that little connection. But once the textbook is already moving, these things start to just glide on top of each other. So there's less force needed to keep it moving.
So let's do one quick example problem before we let you go. So let's talk about a textbook on a table. And let's say that our textbook is 10 newtons. And we want to know what the coefficient of friction is if it takes us, let's say, 2 newtons of force to start moving it. So we want to find our coefficient of friction when it takes us 2 newtons of force to start moving the textbook. So the first thing we need to think about after we've written down all of our givens and our unknown is actually that doesn't really matter in this problem, but let's talk about it anyway. Which coefficient of friction are we finding? Are we finding a static or a kinetic? If we're trying to start moving it, we are finding a static coefficient of friction. So you can add a little s on the bottom there just to make sure that we know what we're talking about. If we're doing kinetic, you could add a k. But for right now, that doesn't really matter because we're not reading it from our reference table. We're trying to solve for it. So what Mr. Petersack is doing is he's rearranging our equation so that we're solved for mu. And mu is going to equal Ff over Fn, our force of friction, divided by our normal force. And when we divide that, can you do it? We get 0.2.
Unit?
None. Notice how he got a number below 1. If you accidentally plugged your numbers in the wrong spots, and you did 10 divided by 2 and you got 5, that should raise a red flag. We cannot have a coefficient of friction greater than 1. So that is a way that you can double check yourself to make sure that you did solve and plug everything in properly.
Okay, so this video actually wound up being a little longer than we expected, but that's fine.
Happens.
So, if you have any questions, please show up to Extra Help and put your comment down in the bottom wherever it shows up.
Maybe the side.
Yeah. And have a great night.